Let's talk about coordinate systems. Let's pick a 3D vector x, say x equals 8, 4, 7. Express x in terms of the basis b equals e1, e2, e3. We've seen these vectors before. These are the vectors that make up the columns of the identity matrix. 1, 0, 0, 0, 1, 0, and 0, 0, 1. So of course, if we express 8, 4, 7 in terms of those vectors, we get 8 times 1, 0, 0, plus 4 times 0, 1, 0, plus 7 times 0, 0, 1. It's 81 plus 42 plus 73. The coefficients are called the coordinates of x relative to the basis e1, e2, e3. And we call this vector 8, 4, 7 the coordinate vector of x relative to b. And we denote it by x sub b. So again, this would be the coordinate vector of x. It just happens to be the same thing as x because the basis we're using is e1, e2, e3, the column vectors for the identity matrix. But in fact, we can express x in terms of any basis for R3. Let's find another basis for R3. Determine if 1, 2, 3, 4, 5, 6, 11, 22, 26 is a basis for R3. Let's use the invertible matrix theorem. Okay? So one way to show that this is a basis is to show that those columns are linearly independent and that they span Rn. Well, if they're linearly independent and they span Rn, then they're automatically a basis for Rn. And the easiest way to show that is to show that the determinant of the matrix is non-zero. So let's look at the determinant of this matrix. 1, 2, 3, 4, 5, 6, 11, 22, 26. The determinant is 21, which is not 0. So it is a basis for R3 by the invertible matrix theorem. And it's a basis because, well, we know that those columns are linearly independent, and we know that those columns span Rn, so they must be a basis. Okay, so let's express 8, 4, 7 in terms of the basis. 1, 2, 3, 4, 5, 6, 11, 22, 26. You got C1 times the first vector plus C2 times the second vector plus C3 times the third vector equals 8, 4, 7. That's just a system of equations. So here's the augmented matrix that corresponds to that system of equations. The reduced row echelon form of this, it looks like this. So here's what our solution is. We have 3, so x in other words, or x1, or really c1, is going to be 3, c2 is going to be 4, and c3 is going to be negative 1. So that means 3 times this vector plus 4 times this vector minus 1 times this vector is 8, 4, 7. And if you do the math, you'll see that it works out. Find the coordinate vector of x relative to b. Well, that's just going to be 3, 4, negative 1, those coefficients that are in front of the vectors for the basis. Let b, b1, b2, let that be a basis for R2, where b1 is 3, 4, b2 is 5, 6. Let x equal, I don't know, just make up something, 10, 17. Find the coordinate vector x sub b. This is the coordinate vector of x relative to b. So again, similar problem, c1 times b1 plus c2 times b2 is 10, 17. We can, in other words, write it like this. And when you just solve the resulting system of equations, you end up with c1 equals 21 halves, c2 equals negative 11 halves, and so this is going to be the coordinate vector of x relative to that basis b. Let's find the vector determined by the basis 1, 2, 3, 4, 5, 6, 11, 22, 26, and the coordinate vector x sub b is 7, 2, 9. So again, we're doing the reverse. Earlier, I gave you a vector and said, okay, find the coordinate vector for this. Now I'm giving you the coordinate vector, and I'm asking you to find what vector that corresponds to. So what vector has this as its coordinate vector? Let's find out. It's going to be 7 times the first vector plus 2 times the second plus 9 times the third. That turns out to be 114, 222, 267. These new coordinate systems can be used in crystallography. Our basis for R3 can be 3 mutually adjacent vectors at one corner of a cell of the crystal UVW. So let's say we have these 3 vectors UVW. Our crystal would look something like that. So for example, find the point 0.5u plus 0.5v plus w. Okay, so this whole vector is u over here, which means we want only half of that. And this whole vector is v, so we want only half of that. So this is going to be 0.5u plus 0.5v. Okay, that's going to take us, 0.5u plus, okay, that's 0.5u. 0.5v is going to take us to about over there. And then plus w, and that's going to take us all the way to the top. So we're going to end up with something like this. Okay, so that's the point that corresponds to 0.5u plus 0.5v plus w. This figure is called a parallelepiped. It's essentially a box which has parallelograms as sides that aren't rectangles, or aren't necessarily rectangles. And they really exist in real life. Okay, Iceland spar, also called optical calcite, is in the shape of a parallelepiped. I bought some examples at a rock shop in Waldrug, South Dakota many years ago, and I trot it out every time I teach Calculus 3. It's very cool to show it to people.